Before 1904, fluid dynamics had a massive problem. The leading mathematical models predicted that aerodynamic shapes would experience exactly zero drag. Real-world engineers building early submarines and aircraft, however, were hitting a wall of physical resistance that the math could not explain. This stems from the no-slip condition. Fluid molecules contacting a solid surface completely halt, trapped by adhesive forces, resulting in zero relative velocity. This triggers a chain reaction. Fluid viscosity causes this stationary layer to slow the layers above it, generating a velocity gradient. Ludwig Prandtl solved the drag problem by dividing fluid flow into two distinct regions. He identified an inside layer highly influenced by the wall's friction and an outer free stream where viscosity effects are negligible and the fluid behaves as an ideal inviscid fluid. To calculate drag, we locate where the friction layer ends. Boundary layer thickness, delta, is defined as the vertical distance where local fluid reaches 99% of free stream velocity. Since velocity asymptotically approaches the free stream speed, this 99% rule provides a strict mathematical boundary. As the fluid moves downstream, the braking effect of that no-slip condition diffuses further out into the free stream. More fluid gets slowed down, meaning the boundary layer thickness continuously increases from the leading edge to the trailing edge. We map this growth across distinct flow regimes. Zone 1 is the laminar zone, defined by smooth, highly ordered parallel sliding layers where viscous forces dominate. Eventually, the flow hits a critical Reynolds number. This triggers the transition zone, where unstable fluctuations cascade. These collapse into the turbulent zone. Inertial forces take over, resulting in rapid mixing, causing the boundary layer to thicken at a significantly accelerated rate. Frictional resistance dictates this growth rate. The exact thickness at any given point is a function of two variables: your distance from the leading edge and the local Reynolds number at that specific coordinate. Even when the bulk of the boundary layer is fully turbulent, the physics change right at the solid boundary. Viscous forces completely overpower inertial forces in the microscopic space near the wall. This physically suppresses turbulence, leaving a hidden laminar sublayer. This creates an engineering trade-off. Turbulent layers generate much higher skin friction drag against the surface. However, their high kinetic energy mixing makes turbulent flow far more resistant to flow separation than a laminar layer. Separation happens when the flow encounters an adverse pressure gradient. Fluid flowing past the crest of an object fights against rising pressure, bleeding its forward kinetic energy to friction until forward momentum halts. When that momentum stops, the layer detaches from the surface. This creates a massive wake region of reverse flow behind the separation point, causing a catastrophic spike in pressure drag. To evaluate these mechanics on the AEE exams, you need this mathematical toolkit. The local Reynolds number identifies your flow regime. Once you confirm the flow is laminar, you use the Blasius solution to calculate the exact boundary layer thickness. Consider this problem. Air flows over a flat plate at 2 meters per second, with a kinematic viscosity of 1.5 times 10 to the negative fifth. Find the boundary layer thickness exactly 0.5 meters from the leading edge. Pause the video here and run the calculation. Remember the sequence. Use the Reynolds formula to verify the regime first before applying the thickness equation. Step 1. Calculating the local Reynolds number gives us 66,666. Since this is below the 500,000 threshold, the flow is laminar. Step 2. We plug our distance and Reynolds number into the Blasius equation, giving us a final thickness of 9.68 millimeters. Now look at the detachment point. At the exact mathematical point of boundary layer separation, what is the value of the shear stress at the solid wall? Separation occurs exactly when the fluid layer at the wall stops moving forward. That means the velocity gradient at the wall drops to exactly zero. According to Newton's law of viscosity, shear stress is directly proportional to that gradient. Therefore, at the point of detachment, the wall shear stress must equal zero. It is important to distinguish the cause from the mathematical indicator. An adverse pressure gradient is why the flow separates. A wall shear stress of zero is the specific mathematical symptom we use to identify where that detachment happens. This reference sheet unifies the core mechanics. It maps the spatial evolution of flow regimes directly against the 4 critical formulas required to calculate them. Master the sequence. The no-slip condition starts the chain reaction. The Reynolds number dictates your transition limits, and boundary layer separation is defined by the moment shear stress hits 0.